This is the last of our theory videos on trig substitution. We're studying the three different types of trig substitutions we can make based off of what type of radical is in our integral. We've studied the type of radical that has a squared minus u squared already, and the radical that has the square root of a squared plus u squared in our integral. In this video, we're just going to tackle the last guy. So what do we do when our integral has a radical of u squared minus a squared, square root of u squared minus a squared in our integral? Well, here's what we're going to do. Let's assume, first of all, that our integral has somebody who looks like that. Like we did for the other two substitutions, we're going to start with a right triangle. This right triangle will have an angle in it. And this guy, because it has a minus, seems to indicate it would not go on the hypotenuse like the square root of u squared plus a squared did, but seems more appropriate that this guy would be on one of the legs. So let's take this guy, let's put it on a leg. Let's say we have the square root of u squared minus a squared on this leg right here. Then if we ask ourselves what seems natural to put on the other leg in the hypotenuse to make the Pythagorean theorem fit well, then I think by now we can easily say that this would be an a, because this is minus a squared, and so this would be plus a squared in the Pythagorean theorem. And this side should be u, the hypotenuse, so that we have equals a u squared in the Pythagorean theorem. So these three edges do satisfy the Pythagorean theorem. So now really the main part is just to find some trig relationship that incorporates theta with the radical and theta with the u. So let's start with the u. If we want a trig relationship that relates the theta with that variable u, then I need somebody who incorporates the hypotenuse. So the hypotenuse is used in sine because it's opposite over hypotenuse, or cosine where we have adjacent over hypotenuse. Which would we choose? I'm thinking probably cosine that uses the adjacent and the hypotenuse. Now we could write cosine of theta equals a over u, but I'm actually going to switch it up. Rather than use cosine, I'm actually going to use secant, and you'll see why here in just a second. If we chose secant of theta, then that would be u over a as opposed to a over u. And now you probably see why I would choose secant as opposed to cosine, because having u in the numerator is obviously a lot better, because now u is simply a times secant of theta. So let's box that in. So if you have an integral that has some radical terms and you need a substitution to make for the variable expression, use this, use a secant theta. All right, now who would be good for the radical expression here? Well, theta is right here, and so the radical is opposite theta. So the trig expressions that use opposite would be sine, opposite over hypotenuse, and tangent, which is opposite over adjacent. I think I'll use that one because same as before, I'd rather incorporate theta, the radical, with the simple constant, simply because the math would be easier. So we'd have tangent of theta would equal the radical of square root of u squared minus a squared divided by a, or the square root of u squared minus a squared would equal a times tan theta. You see what we did here? We just simply moved the a over here to the left hand side. So let me box that in as well. So these are your two guys that you need to know. If your integral contains somebody like this, then you'll use the a secant theta substitution for the variable expression and a tan theta for the radical expression. Now again, I've said this in the last two videos, but I'll repeat it again here. So I'm sorry if you're tired of hearing me say this, but most textbooks, it will give you a chart, and they'll say if your integral contains somebody like this, then you do this and this. But that's a lot to memorize, so make sure that you get proficient at doing these on the fly. When you see an integral that has somebody like this, you don't have to remember all this stuff. Draw yourself literally on your paper on a test, draw a right triangle, put him on an edge, figure out who the other two guys are, and then make your substitutions, right? You'll be a lot better off, because you can even find this a year from now. You're not going to remember what you memorized a year from now, but you can remember the logic behind it. And so there you go. That's the 3 techniques. We're done with the theory now. So now going forward, what are we going to do? Well, now we need to try some examples. And so we'll work through a few examples where we try, some of the first type, some of the second type, and some of the third type. So now that we're done with the theory, you can kind of move on to some of the example videos.